Hey guys, it's Milo. This is Matlab video tutorial number 5, and today we're going to talk about for loops in Matlab. I have right here a really simple example of a for loop just to show you how it works, and then I'll run through another example where I show you how to take a derivative with a for loop. Alright, so if you're going to use a for loop, you're going to be writing for an end, and you're going to be writing some stuff in the middle. Basically, the way this works is there's an indexer. In this case, I'm calling it I. It appears directly after the word for, and you're going to set it equal to a vector or an array, whatever you want to call it. And in this case, I set it equal to an array with the numbers 1 through 10 in it. And what it's going to do is it's going to run through the statements inside the for loop, and it's going to set I equal to, it's going to start with the first element in the vector, and it's going to run through the statements with the first I, and then it'll run through with the second I, and so on until it's used all of the elements in the vector. So if you just write 1:10, you get a vector that counts from 1 to 10 in increments of 1, which is it's really like a compact form of this guy, where you have 1 colon and then maybe 0.5 colon 10. And this will count from 1 to 10 in 0.5 increments. If you leave out that middle term and just write it like that, then it assumes you want to count by 1. And this is the form that most vectors that go into the first part of a for loop look like. You usually know how many times you want the for loop to run. So let's just say n equals 100, and that's how many times we want it to run. So you would do something like 1 through n. So let's do that here. So the for loop will run until it hits n. So the statement inside the for loop right now it's kind of trivial. It's just I squared essentially. So let's go back to 10, and we can kind of guess what it's going to look like. Each element in A is going to be I squared. So the fifth element of A is going to be 25, and the ninth element is going to be 81, and so on. And let's just run this and make sure that we get what we thought we would get. Oh, whoops. A. There. So 1 squared, 2 squared, 3 squared, 4 squared. Cool. So that is the basics of how the for loop works. You don't even have to go in increments of 1. You don't have to increase in increments of 1. I could write the for loop to look like this, to go in increments of 2. I could write it to go in increments of 0.04 or whatever I want. The only thing is, if I want to put these answers into a vector, I can't use I to index where they go in the vector anymore. That's why it is convenient to have your counter, in this case I, increase by 1 every time, every iteration of the for loop, as opposed to increasing it in this way. And there are other ways. If this is actually what you do want to accomplish, there are other ways to accomplish this without messing with I as an indexer. Alright, so now I'll show you an example where I'm going to take a derivative using a for loop. So you guys are probably all familiar with an approximation to a derivative. Rise over run will approximate the derivative reasonably well if the function is pretty well behaved. So we want to kind of automate the rise over run process and put it in a for loop and essentially sweep from left to right across our function and build up the derivative to the function. So we're going to take the derivative of, you can do anything you want, but I'm going to do a sine function because it's easy to check the answer because we know what the answer is. So it's really easy to plot our approximation to the derivative of sine and then check it against cosine and make sure we did it right. So here the red curve is going to represent the y value of the function that we want to take a derivative of in this picture, this little example. In the example right here, I'm taking 8 points and I'm seeing what the y value of the function is at each one of those points. So each one of these points has an x value, and I'm evaluating sine at each of those x values. So there's 8 points, right? And then there's 7 intervals, and we're going to be approximating the derivative over the 7 intervals, not necessarily at each point. So there's going to be, in our answer, there's going to be one less element than there was in the input. So the output has one less element than the input, which is fine as long as we know what's going on here. So rise over run, that's the difference in y over the difference in x. And so if we wanted to do that over the 6th cell, the 6th interval right here, so 1, 2, 3, 4, 5, 6, then it would be the 7th y value minus the 6th y value over the 7th x value minus the 6th x value. And you can kind of generalize that by saying that the change in y at the ith interval is yi plus 1 minus yi, and similarly the change in x at the ith interval is xi plus 1 minus xi. So if we wanted the first interval, if we say I equals 1, then that's y2 minus y1 over x2 minus x1, and that's correct. And so our approximation of dy dx over the interval I is going to be dyi over dxi. So let's see if we can't put this into a for loop. We'll do some setup work first. We want to approximate the derivative from 0 to 2 pi. So you can see my x vector right here. I'm using linspace, which means that the space between all the x points is going to be the same. So we don't even need to do this this step xi plus 1 minus xi because it's always the same. Dx is going to be basically 2 pi divided by, so we have 101 points. That means we have 100 intervals, and dx is 2 pi divided by 100. We're going to solve for the derivative between 0 and 2 pi, and our x vector has 101 points. NP is number of points, NI is number of intervals, NI is NP minus 1. The function that we want to take the derivative of, you can make it anything. I'm making it sine x. You can make it any function of x. It could be a trig function. It could be trig function mixed with other stuff, x squareds. And then this is where the answer is going to go, dy dx. It's just zeros right now. And it is it has ni rows. It has 100 rows, not 101 rows. So that might be an issue for plotting, right? Because we want to plot something that has 100 elements versus something that has 101 elements. And that arises because we're approximating the derivative over the intervals and not necessarily right at the points. But it's cool for now. It's totally cool. All right, so the for loop. We're going to use I as our indexer again. We're going to go from 1 to ni. The reason we're going to ni and not np is because if you look inside the for loop, we have an I plus 1. And if you think about it, if we went to np, if you plug in 101, that means the Matlab would be trying to access y, the 102nd element of y, which doesn't exist. So automatically, you should know that there would be a problem there, and we really want to go from 1 to 100 in this case. So here's our dy, y I plus 1 minus yi. Dx we kind of pre-calculated because it's the same every time. It doesn't need to be inside the for loop. So then dy dx at the ith interval is dy divided by dx. And it's going to just march on through. It's going to start with I equals 1. It's going to go until I equals 100. And put all the answers into this array dy dx. And then we're going to plot it. So like I was just saying, dy dx only has 100 elements. X has 101 elements. One way to rectify the difference in number of elements would be to make a new x vector and have kind of the midpoint of each cell in your x vector, and your answer might look a little better, be a little more accurate. But we cut these slices pretty small. I'm going to not even think twice about just for plotting purposes lopping off the last element of x. So you can see what I did here. X from 1 to n minus 1 essentially cuts off the 101st element of x. So now this guy and dy dx are the same size and can be plotted together. And then we'll plot x proper with cosine x and make sure that the blue line and the red circles kind of look the same. And here you have it. You can see the blue line really should be shifted over a little bit, and plotting the blue line at the center of each cell instead of at the beginning of each cell would probably take care of that. But it's really close, as you can see. So our for loop worked. Our approach for taking the derivative did a pretty good job, and hopefully you know a little bit more about for loops now. Have a good one.